Okay, future me. So this is how differential equations works. Partial differential equations. So this is the function. Okay, so let's start at the beginning. This is the equation. There is some value t that changes with respect to time and also changes with respect to x. It doesn't matter that it's the second derivative. This is a constant, right? And the domain is t is greater than 0, so that means that it starts at 0, right? And the x domain is 0 to L. That's why on here we have 0 to L, right? And so the boundary conditions, the partial derivative of t with respect, so basically what this means is that the slope at 0, at x equals 0, at any point is 0. So right here it's 0, right here it's 0, right here it's 0, right? So every single time that we have a new t, we need to apply this boundary condition, okay? And then this boundary condition, t at x equals lt, is 0. So this means that the value, the function value, this t, is always 0 on the x-axis at x equals, or at L, right? And that's at x equals m plus 1. So we do the delta x is L over m, right? We want a certain amount of data points, so we have the length divided by the change, or yeah, whatever. And then, see, we have that here, right? Step 2, this is approximating this in this function, right? So we use the second order 3-point central difference formula, which basically just approximates the second derivative of this in terms of x. And so these functions, these values right here, these are going to be these values, right? So this is just in general. It's not going to work for the first point right here. It's not going to work for the points right here, right? Because we don't have t1 minus 1. And so the function value at x1, which is 0, the function value of this is always going to be defined by this. And so we can assume this partial, or this derivative, we can use another difference formula right here. So this is the, this is the 3-point forward approximation for the first derivative. And so we set that equal to 0, right? Because that's the boundary condition right here. That is equal to 0 at x equals 0 t, right? So that's 0. So that gives us a value for t1. This is the value of t1 that we use for all of these, right? So yeah, so this is the t1 that we use for all of these. And it's dependent on this and this. And then to incorporate this boundary condition, tm plus 1 is equal to 0, right? So yeah, we approximate the function using this for any non-beginning point 1, right? So like at x equals 2, this approximates the derivative, the second derivative. And so then we incorporate the boundary conditions, right, like I just told you. And then step 4 is when we put it all together. And so then we use, this is where we use the like Rubna cut or whatever, the, where are they? These, like the numerical solutions, right? This is where we use this. So right here, I'm using a forward method, right? And so this value at t of j plus 1 x of I. So x of I, let's say it's 2. This value right here, this is this value. So we're using the knowledge of this function x at the initial condition, right? We're using this knowledge to find this next value at this x point later in time. So every x point is going to have a different equation, right? Every x point is going to have a different equation that's governed by this. And so then this is approximated as the initial one, this one, right? The value right here. which is t of tj xi. This is tj xi is 2. So it's whatever that value here plus h, which is delta t, because we're doing tj plus 1. So it's the change in t, times the whatever constant, times this approximation, which is this approximation, right? So you evaluate this, so that's like ti plus 1 minus 2ti plus ti minus 1, right? Delta x. And so that gives you this next value. And since it's a system, that means that then we would have x3 would give us different t values, right? Because you would have this one, and then this third one, right? So that gives us the different t values. And then that's going to give us the next one of here. So you need to do all of that in order to then do the next step, right? Because you need to have all of these t values that initially were given because of the initial condition. But now we need to find them all. I hope that makes sense. I think I should remember because I'm known for a good memory.